Again. Hello and welcome. I'm Matthew Forman. I'm Head of Bioinformatics and Software Development at Yourgene Health. We're an international molecular diagnostics company in the areas of reproductive health, oncology, precision medicine, and infectious disease. And I'm going to talk to you today about flex analysis, a safe, integrated, and flexible approach to non-invasive aneuploidy analysis. So, a brief summary of what we're going to go through. Firstly, I'm going to talk a bit about software in sequencing test workflows in general, the roles of software. We're going to do a quick tour of the key user needs that we find have always come up in this area. And then we're going to go on in part two to a study of an NIPT type workflow. We're going to have a bit of a focus on NIPT analysis to see how all the major parts work. We're going to talk about how we can meet those key needs that I would have talked about before. A little bit about workflow management software as well. And then the final section of a conclusion plus a little bit of looking forward to what we see coming in the future. So to start with, the software and NGS test workflows, or as we really ought to be calling them these days, just software and sequencing test workflows. So the roles of software. For any test whatsoever that involves sequencing, we have software actually appears in a number of places. Most obviously, we've got the bioinformatics analysis section in the top right corner there. Which is right at the end of the chain after everything that happens in the laboratory. So obviously we're going to start with a sample. There's going to be an extraction or isolation stage. There's a prep stage of some kind, and then there is sequencing. And then whatever comes out of the sequencer, all the reads that come from the sequencer need to go into a bioinformatics analysis software stage. So that's the most obvious place that software is going to be involved. Also, we have and I've shown these things in dark blue on this slide. Also, we have a lab and workflow information management system, which cuts right across the whole workflow, including the analysis section. So that integrates all of the instruments, handles all the data flows, and provides tracking for samples, and also things like business reporting and monitoring functions. There is a clinical data management function as well. We need to get the patient and sample, the test request, and so with the patient and the sample metadata into the lab in the first place. And we've got to get the report and the results back out again to the right place. So we need a system that can handle that data transfer efficiently and accurately. And there can be a middleware layer as well, so which I've kept not quite in the same blue color. It's optional, really, in many ways. The middleware stage, the middleware system is normally a connectivity layer, but very often the workflow management or lab information management system actually handles all of that. In very complex environments, there will be more middleware, but as you can see, there are quite a few places that software is going to appear in any lab test environment. Just going on really to the key needs of any piece of software. So whatever of those functions it's doing, there are some things that it absolutely has to do. So obviously, the basic functionality that the software has, the basic functionality of the test has got to be delivered robustly. That's always number one concern. And when a new system is in a research and development phase, obviously the very first thing you're going to look at in feasibility is, can we actually get it to generate the results that it's supposed to, and do it in a robust way? But we also there are some really critical needs that we've identified through the years as well, that I guess you could say have not always been at the forefront, particularly when a new type of test analysis it has arrived. A new kind of system is on the horizon. But these things, really, we really mustn't lose sight of all of these key needs. And I'm going to go through really where these come in and why they're so important, and the impacts that they have on the system and on the process that you use to develop the software systems. So firstly, safety. Now, this means both patient safety and user safety. In the end, when it comes to software, there is so much more to software development than writing code. I mean, all you have to do is to look through an app store, look at the update text against a favorite app that you might just be downloading an update for, and how many of them are going to say bug fixing. Quite a lot of software that's non-clinical, non-medical, or that doesn't run other safety critical systems does not. It generally is, arguably some of it's released a little bit early, and us users end up doing some of the bug fixing for the developers, or rather identifying the problems and feeding back to them. Obviously in clinical or IVD applications, safety is critical, whether you're talking about the patient safety or whether you're talking about user safety. With software, user safety arguably doesn't come into it quite as much as it may do with an instrument that's got motors and is physically moving things around. But the way that we do these things will always bring, into the risk analyses, will always bring both patient safety and user safety. Ultimately, because software bugs in medical software can lead to wrong or inconclusive results. And the end result of that down the line could be harm to the patient. They could perhaps not be identified as needing to go down a pathway that they should have been, or they may end up going down a clinical pathway that they should not have done. So it's important that obviously, above all else, that steps are taken so that bugs, even if the analysis of the system, it's fully tested, it's been verified and validated on thousands of samples, and everything works fine, there is still a possibility that a software bug could mean that the system doesn't do exactly as it was intended to do. So it is critical that that's all taken account of. So that's really mainly what we mean by safety. And if we have a carefully controlled and risk-managed development process for software, we can mitigate these software risks and identify them and make sure that they're not going to cause problems down the line. So I'll say a little bit more about that last point, actually, just in a moment. There is one, I guess another little thing to say on this is that if you don't have a controlled process, there's always going to be a risk that there are unseen, latent software errors that could cause problems. And that's actually further exacerbated if you have a lot of SOUP standing for software of unknown provenance. Essentially what that means is anything that hasn't been developed by the team that's doing the core development itself, that's developing the software itself. So if they're bringing in components or libraries from outside, anything they haven't created themselves. In many cases, some of that software may not have been written or tested with medical safety in mind. You go out of your way to try and find solutions that always do, but ultimately code that's written by someone else under a process that you don't know is inherently risky unless you thoroughly validate it. So the path that we have to go down if we're not writing all the code ourselves is to make sure that all of those relevant functions are fully risk assessed and fully validated before we go any further with them. But what can we do to control all of these? What are all of these risks? What does a risk management development process actually look like? So there is a standard for it, of course. There's a standard for everything. ISO IEC 62304 is an international standard, and it specifies all the necessary elements of a controlled medical software development process. So it covers, for example, specifying design inputs, collecting the requirements, making sure that we've got everything in mind that the user needs, design and implementation, coding, the required testing methods. So how do you go about, or how could you go about making sure that the software is tested at the point that it's developed, is tested with other components of the system, and then that the whole thing is validated together with the final workflow. And then it also interfaces with the risk management work and the usability work that goes on. It has interfaces to other standards in those areas. It doesn't tell you exactly how you have to go about doing that, because there really needs to be quite a lot of room for maneuver in exactly how you manage the software development process itself, but it does specify what the minimum elements are, what elements have to be done at various different risk levels. And ultimately, the focus is always going to be on, the whole point of this is on minimizing the risk of harmful software errors. And that any other software error that might occur, if it's not harmful, we at least know what it would do. We know what the ultimate impact of that would be. And in the end, what it means is that you get the highest quality software product out of that. And it gives confidence that the software will behave only in known ways, only in ways that it was designed to do. And very usefully, this is ISO IEC 62304 is aligned with regulatory requirements internationally. So, for example, the requirements of CE-IVD in the European Union, the FDA requirements, it's a harmonized, and various other requirements as well. It's a harmonized standard in that way. So moving on from control of software processes and how you ensure safety and risk management that way, into flexibility. Because, doesn't surely regulated software development, when we go through all of those processes, standardized processes, doesn't that mean you end up with something quite monolithic and static that's very time consuming to change and therefore probably quite expensive to do anything with? I mean, after all, some changes that you might want to make to a system are pretty common. Arguably, they shouldn't take a year and cost hundreds of thousands of dollars to do that. So, a few typical examples of the changes that we commonly that we have before commonly had come in. So very often, customers will want different reporting or result formats tailored to their own local needs and their local conditions, or maybe their local regulations. They may want, this comes up quite often actually, they may want the software pretty much as it is, but just a slightly different look and feel, different styling. That might mean that they could have their logo in it, for example. It might mean that they need to use house colors. It might just mean moving a few elements around in the user interface a little bit. There is often a request to extract some test metrics that the system may not normally give because they're not needed as part of the validated test workflow, the analysis for the fully validated analysis for the test workflow itself, but maybe they're needed for local reasons, for monitoring, so that post-market surveillance can be done according to the local needs. And there may also be a need to communicate with external systems that outside this particular test workflow that we're talking about. The next on the list of key needs really is usability. Sorry, that's it. Right. The next is usability. So when bioinformatics software really first came into being and started moving into the laboratory, it was coming in from a research environment. So freely available tools had been developed. Quite a lot of we have a lot of bioinformatics tools that are contributed to the community as with the source code, written mostly in a lot of them in research institutions, and we wouldn't have anything like the valuable contributions that we've had to the field, and it wouldn't have been possible to develop a lot of the workflows and the tests that we have done without those. But they're not necessarily suited to commercial operational lab environments because they were normally created without medical grade code or development processes. So that also means that very often there was a limited level of integration with lab systems. User experience was not always a focus, so a focus on getting a test up and running to begin with, getting the analysis working is on exactly that. Quite rightly, it's on getting it working. It's on showing that it works and that it works reliably. But sometimes the usability of the interface to actually control that analysis has not always been kept pace with just how good the system itself is. And then some rather limited, often clinical data entry and reporting capabilities. Sometimes you end up having to enter the data into a system via a spreadsheet, for example, and then extract the results from maybe another spreadsheet, and then mail merge them onto a sort of word processing package to get a test report. So not quite always as integrated as software could be on those fronts. And then also the other thing about usability is it does have an important interaction with safety. So ISO IEC 62366 is another standard in that area. And that's about designing user interfaces and user experiences to reduce the risk of errors and make sure that safety isn't compromised through misuse. Usually the outcome of risk analysis work and user panels, user focus testing, that kind of thing. Next, we've got connectivity and confidentiality. So lab software, of course, does not operate in isolation. The data flow between the various elements needs to be seamless, but it also needs to be reliable and robust and secure, because we're talking about confidential information here a lot of the time. And there are a number of things we can do by design, and also a number of things through policy on that front. So by design, we would try to make sure that we used secure data protocols everywhere. Certainly, absolutely everywhere where there was any kind of movement of the data outside the system, it's absolutely critical. But inside a local network, wherever possible, we anonymize data that we store where possible, and we only include fields in a database that are actually needed. And we do things like develop parts of the system that will automatically delete data after a certain amount of time, after a certain expiry time, when the test has run, so that it isn't hanging around longer than it needs to. Also, you can design in standards to maximize various benefits for connectivity and confidentiality. So you can deploy standards like HL7 and FHIR, for example. And then through policies, I mentioned destroying data when it's no longer needed. Try and do that automatically where the system can do it, but have policies where it isn't. Appropriate network security with access control policies, and plenty of system and data backups, of course, so that if any data is lost, it isn't for very long and it can be brought back. So those are really the key user needs that through much time in this area we've identified as really important when it comes to putting software systems together that really work well on the ground. And I'm just going to spend a bit of time now talking about an NIPT workflow as a case study of some of these aspects. So I'm going to use the Yourgene Flex modular analysis platform to illustrate some of those concepts that we've just been talking about. The Flex analysis platform is constructed as a set of interconnected communicating modules. They're all those little boxes with the grey background behind all of them. Each of them has got a defined boundary with its neighbours and interfaces for communications with them. But importantly, it looks to the user like one system. It looks like one monolithic software system with one interface. But behind the scenes, it's actually built of several modules. Modules are split. We have modules that are split into either customizable modules or core functions. So there are some core functions that are always included, and those are on the left-hand side of that diagram. They might be, for example, modules that split up sequencing data into multiple samples when it was multiplexed into one sequencing run. There could be a fecal fraction estimator is an important QC aspect of this kind of analysis. Alignment to the genome. Of course, generally, whatever sequencing-based workflow you're using, there will need to be an alignment to a genome, whether the human one or another genome, at some point to identify where those reads are absolutely most likely to have come from, so that we can then do the further processing on them that we need to. That's the case whether you're talking about a whole genome test or a targeted methodology. And the customizable modules, typically things like those that calculate the final risk score or probability scores for the test. Those that generate the report can therefore be modified to suit the local conditions. Some QC checks. It depends very much on what instruments you've got and what those are doing as to where the points in the data that you can check against various thresholds to make sure that everything is working in line. But I'm just going to go into now a little bit more about these and talk about how we can meet those needs that we identified earlier. So the basic steps in an NIPT analysis pipeline, what the pipeline ultimately does is it robustly processes the sequence data, combines it with the patient and sample information, and outputs a clinical test report. And it does that by firstly reading and filtering the sequence reads, mapping those reads to the genome, and analyzing the DNA location data, and it does that through a number of statistical model, machine learning or AI-based methods. And it then calculates the test results and applies the QC checks on those just to make sure that everything is in line. And if it isn't, then reject the result. And then finally, it generates the test report, which can go back into the rest of the system. Moving on, meeting those needs. So how do you then ensure? We talked a bit about software safety and software safety standards before. What you've got to do is explore the user requirements in full and document them thoroughly, but then operate in short sprints. That means that you can then respond to slightly changing user requirements. And we would run user panels and show people what the GUI looks like, use wireframes, that kind of thing, to get feedback whenever we can. Separate the algorithm design from the software code implementation. We've got to try and demonstrate first that the science works 100% on the bench first. So the analysis actually does what it's supposed to do before we go anywhere near writing code for the application itself. Test, test, and test again. I could say test again. You really can't say it enough times. One software testing methodology is not enough. You've got to do it in small blocks, very close to the coding first, then full modules, interconnections of modules, and then finally validate the whole system, ideally with samples where we don't actually know the outcomes until afterwards. And we risk manage the process throughout. So prevent system errors and failures impacting accuracy and safety. And it's all according to those standards I mentioned before. Well, one of them I mentioned, 62304. There is also 14971 risk analysis and ISO 13485 for the overarching quality management system, of course. On to usability. Firstly, always consider the customer requirements or user needs first. And that's clinical or operational. So it is talking to the healthcare professionals. It is talking to the people in the labs who will use the systems as well. Fully consider the wider context and the environment of the software. Things like connectivity come into that, and confidentiality. Maximize usability overall is the message here, which is a key principle for us. Ease of use, effective systems and integration, and seamless data flow are then what we need to get out of those. Flexibility, so it doesn't have to be at odds with safety, with software safety. The way that we make sure it isn't at odds with software safety and that you can have your cake and eat it is that new software deployments use already developed and pre-verified medical grade algorithms and software modules. So by developing those modules individually and testing them individually as far as possible and risk analyzing all of their inputs and outputs individually, we can then plug them together in separate arrangements, and we can develop custom modules if necessary to fill needs that maybe the system doesn't have to begin with. The customizable modules that are available as well are for example, some analysis plugins. Analysis plugins can be written to implement different kinds of test algorithms. For example, to add onto a basic trisomy analysis, you can add sex chromosome aneuploidy analysis. You can add microdeletions. There are various alternative test algorithms that we've already implemented through these plugins, and more can be done. Theming plugins to customize the user experience and make the system look the way that it works best locally and the way that the local users want it to look. Test reporting, fully flexible content and format so that you can have the form that makes up the report contain what you want it to contain and where you want it to put it as well. And going right through to font sizes and where the logo goes and what ancillary information goes on it and all that kind of stuff. And as I mentioned, the system can support fully custom modules. If you do it this way, the system can support fully custom modules if needed to fill in specific needs. Onto connectivity. So one way of doing this is to build in a purpose-designed LIMS interface based around a common standard, HL7. And that defines a standardized language to communicate both incoming requests for tests and outgoing requests and test reports. So that's rendered reports or raw data fields. And I've drawn a very heavily abbreviated version here, just to show you how the connectivity of this could work. So we have another software system called the Atlas Workflow Manager, which is it's kind of I'll talk about it a bit more in a moment, but it's a custom LIMS that is specifically designed to manage in detail the kind of test workflows I'm talking about. So the request could come from a laboratory LIMS into that system via the HL7 interface. Once the test is complete, the Flex analysis system can upload the result with a copy of the PDF report, if necessary as well, back to that LIMS again, where it can get associated back to the original request. Nobody then has to type anything in again. Nobody has to read something off one system and type it into another. You don't have interpretation of forms and then typing back into other systems, which obviously wastes a bit of time and could be quite error prone if you address this kind of connectivity. So Flex has got this purpose-designed LIMS interface to meet as many of those connectivity needs as it can. And finally, robustness. So design QC checks around the key measurements so that you can identify when something goes out of band. It allows automated reporting of workflow and sample conditions. There are a few examples from NIPT here. So typically you would want to measure the cell-free DNA fraction and fail for that sample if there is insufficient signal to call confidently. You'd also want to measure the sequencing output. Have you actually got enough reads to call confidently? And very often we would consider those two things, we can trade those two things off against each other because it's very important to make the best use of the information that you've got available. So for example, if you have a really high cell-free fetal DNA fraction, you don't actually need as many reads and you can still get just the same accuracy out of the system. So it's best to consider those things together. And you can do things like read metrics from the sequencer. So, for example, the Illumina systems will sequence a PHI-X control or recommend that a PHI-X control is put into every sequencing run. We can read the data from that, and it gives you an extra metric that can identify low-quality sequencing output so that it doesn't then cause a problem. A little bit more about workflow management that I mentioned before. So, the Atlas Workflow Manager is a system that gives full sample traceability from bringing a sample into the results analysis. It's like a special purpose LIMS that manages the test very closely, and it integrates the instruments and analysis into a virtual workflow. It means you don't need complicated worksheets and frees up a lot of operator time. It can even tell you when you put something in the freezer and where in the freezer it is. It'll print sample labels automatically and manage all of the storage of all of the materials that are part of the test. And so just to finish off with, really, I've got a few little screenshots that I'll just run through very quickly. Firstly, on the workflow management front, I know it's not the easiest thing to read, but hopefully you can get a feel for it. The Atlas Workflow Manager input. This is one of the input screens. We have on this particular system here, we have a theme loaded that makes the system look a certain way. It's using our house colors here. On this page, this is where you would start receiving a test order. So enter details of the institution that requested the test, some information about the patient, and scroll down and add in all of the rest of the demographic data. assuming you hadn't downloaded it from a LIMS, of course, an external system, which you may have done, and then of course you wouldn't need to type it all in again. Here's a tracking screen. So here what we've got is some 16 plasma tubes are sitting on an instrument. We've opened up the instrument to see what's on it, and it's telling us that there are these 16 tubes, and then we've then opened up the second one, and we can see what test that is for, the name of the patient, the institution, and any notes that we might have added. And we can drill down further into that if we need to. On the analysis side, finally, on the analysis side, really just a front page, this one, but using a different theme. But you can click through to a test status page from there, or you can click through to enter sample information, assuming it hasn't come in automatically from another system, like the Workflow Manager or the LIMS. And there's a little configuration and data export button in the bottom right there as well. And then here's one of those test status pages. So it's showing that there are 3 tests on the system at the moment that are going through. There'd generally be a lot more than that, of course, but this is software testing data, not real world data on this particular screen. So it's telling us who the test is for, it's giving us an ID for it, and it's got a button to go through and edit the sample information and create the report. And it tells you what the status through the workflow is as well. So that's pretty much all that I have for today. I've got a little bit of a conclusion and a bit of looking forward as well, with a couple of interesting directions that we can see that this area is going to go in. So, as a summary, software fulfills several key roles in an NGS workflow. Whatever the role, there are always going to be these key needs of robust functionality, safety, usability, confidentiality, connectivity, and flexibility. Flex Analysis is a platform from Yourgene for NGS Bioinformatics analysis applications. It's a platform, so the idea is you have the core analysis functionality, but there are also these customizable components that you can change. And the Atlas Workflow Manager integrates instruments and analysis into a virtual workflow. This is what we have here is one way in which you can meet all of those needs. Looking forward, so some interesting things that I see going on here. There are definitely many signs of a broader move from one-off software solutions that do one thing to much more flexible platforms that can integrate much better with other lab systems, clinical systems as well, but all still with robust validation, so that you have high confidence in the system and full regulatory compliance, including the software having been developed that way. And there are also some interesting updates coming to the software regulatory frameworks themselves. There is work going on that looks like these standards in the future will probably reflect more of an evolution towards standalone software. Software development standards in the past have mainly been concentrated more on firmware more than software. So the kind of code that sits inside a machine, such as an ultrasound machine, for example, less than standalone software. But there's more of an evolution towards standalone software because there's so much more of it being used. And also there's very interesting work going on to adapt these standards so that we can bring in more machine learning and AI techniques. A pretty difficult thing to do with the software, regulated software development process as it is, because if a system is learning for itself, how do you validate it? How do you control exactly what it's doing? There is some guidance now available from the FDA in how that can be done, and the European institutes are working on in a similar kind of area. It hasn't made it into the standard just yet, but there's a lot of interesting work going on in that area. And we need it to, because we need to bring in the latest techniques. We need to bring in the latest and most accurate techniques into medical grade software development. Thank you very much for listening.